Hi, my name is Yeshan. Let me introduce myself briefly first. I am from Sri Lanka and I have a PhD in mathematics, concentrated in statistics, and currently I work as a quantitative risk modeler for a leading bank in the US. I obtained my bachelor's degree in mathematics and I have an MBA in finance. Both are from University of Colombo, Sri Lanka, and also I completed my master's in mathematics and the PhD from Ohio University in USA. Okay, so today's lesson is a continuation of logistic regression in the curriculum of biostatistics designed for African Institute for Professional Development. In this lesson, I will briefly introduce the definition of binary variables first. Then we will discuss about the linear probability models to get an approach to introduce logistic regression model, the main focus of this lesson. Next, we will discuss about measuring how good the fit is, how to make a predictions using logistic regression, and how to extend the idea to include multinomial responses as well as an ordinal response variable. Okay, so let's begin. Let's start with the understanding. Let's try to understand the binary variables first. So consider an experiment of flipping a coin. How many how many outcomes can we get from the experiment? So what do you think? So we can have only two possible outcomes, head or tail. So for example, if we count the number of heads, we can have uh, from a single coin flip, then it is a binary random variable because we can have only two values, 1 or 0, right? So we flip the coin, then we can have either head or tail. So if we count the number of heads, we can have only one head or no heads at all. In this particular case, our success is getting a head. So the probability of success is 50%. Here we assume the coin is fair. In statistics, we call such a binary variable a Bernoulli trial. Now suppose you flip the coin 10 times and count the number of heads you uh, can get. In this experiment, the number of heads you can get is also a random variable, but it has more than two possible outcomes. In fact, it can take any value from 0, 1, 2 up to 10. So 0 means you don't get any head out of the 10 trials. 1 means you have exactly one head out of the 10 trials. 10 means you have head in each trial. Note that this experiment is a combination of 10 independent Bernoulli trials. And the variable we constructed is called a binomial random variable with parameters 10, that is the number of trials, and 50%, that is the probability of success. So binomial distribution has two parameters, n and p. N is the number of trials and p is the probability of success. Okay, now let's consider the linear regression model. I assume that you are familiar with the linear regression model. So if you just think about it, usually in a linear regression model, we have a continuous response variable. But think what will happen if we replace this continuous response variable with a binary response variable. Like we try to model the status of an ill person after a medical treatment. So we need to know if this person is recovered or not. So it has two possible outcomes. So that's why we call it a binary variable. If we simply use the linear regression model with this binary response variable, we will get the so-called linear probability model. This model is very interesting because it says that we can estimate the success of the probability of success, that is P, by using a linear combination of independent variables, which is very easy to interpret. Because in this case, you can see the linear regression model. This linear regression model here, we have the linear combination. And when we replace this conditional expectation with the probability, we get the linear probability model. So it says that we can estimate this P by using a linear combination of predictors or regressors. So this linear model is very easy to interpret, but the problem is it correct? Can we really estimate the probability by using this linear probability model? So what do you think? So let's see. Now to answer this question, is this model, can we use this model to predict the probability? Actually, the answer is no. Why? Because the linear regression model can predict the probabilities which can go beyond zero. Yeah, that means less than zero, or it can go beyond one, that means more than one. So we all know that the probability should not be less than zero or more than one. And on the other hand, uh, the binary response variable is a discrete random variable. So it is not continuous. So it doesn't have a normal distribution. So this linear probability model actually does not satisfy most of the underlying assumptions we have in the linear regression model. Therefore, this model theoretically does not make sense to estimate the probabilities. Like, for example, if we, for example, this model can predict the probabilities less than zero or greater than one, as I said earlier. So that's why it's not a good model to estimate the probability. But it has good um, good qualities, we would say. Like, for example, this linear probability model is a good screening tool to modeling, and coefficients are easy to interpret. So you can, even though this is fundamentally wrong, you can use this model to see how the coefficients, if the coefficient are big enough or something like that, just to see how it is working with the regressors that we are thinking of. And it has these problems that I mentioned. So now we will see how we can use this idea of linear probability model to estimate the probability by doing a transformation. Or if we can restrict this P in between 0 and 1, then we might be able to use this model. So let's see. Okay, so we just saw that the linear probability model is a promising tool, but it has its own problems, such as the probability can be predicted to be less than zero or more than one. So let's see if we can address that issue and make it a useful tool to predict the probabilities. For that, we can use this logistic transformation, which is a very nice uh, transformation that you can see. So here you can see that in this graph, so in this graph, you can see that for any real number, if you apply this transformation, it will give you a curve like this, which is restricted in between 0 and 1. So this transformation is called the logistic transformation, or sometimes we call the sigmoid function. The sigmoid function is very popular in neural networks and in many other uh, applications. So this transformation is a handy tool to know. So if we can do this by using logistic if we use this logistic transformation, sometimes we call this as the sigmoid function. And so here you can see that the sigmoid function is a one-to-one function, right? So that means we can take the inverse function of this without having any theoretical issues. And once we take the inverse function, we call that inverse function is the logit transformation. So what we're going to do here, so if you just think about this linear probability model, here you can see that the probability is explained by the linear transformation, but this can take any value. So we try to use this side with the logistic transformation, then it will be restricted in between 0 and 1. And then when we apply this into the linear probability model, we can get the logistic regression model as follows. So let's see how we can apply the logistic transformation to convert the linear probability model so that we can make sure the estimated probability is in between 0 and 1. And now by using the logist transformation, we can get the logistic regression model, which can be estimated using the maximum likelihood method. Maximum likelihood method is beyond the scope of this lesson, so I will not discuss about maximum likelihood estimator here. So if you are wondering how did I get this one, um, it is like this. So you can see this this linear combination. So that is my left hand side of the linear probability model. So I apply this. I consider this. Let's say this is some. Let's give this a name. Let's say A. So I apply the logistic transformation. Then you have this e to the power a divided by 1 plus e to the power a. Or you can have like 1 divided by 1 plus e to the power minus a. And then when you do the transform, when you apply the logic transformation for this function, you get this logit conversion. It gives us this relationship. You can try this and see if you can get this form by yourself. So this actually, just by doing some little algebra, you can get this stuff. So, so this is the logistic transformation, and then by applying the logit, the inverse transformation, you can get the logistic regression model. So it gives you this. So here you can see now the natural logarithm of the probability divided by 1 minus probability is equal to a linear combination of the predictors. So this form is really important because this side, this linear combination is very easy to interpret. So these coefficients are easily interpretable because of this form. And how do we estimate this? By using the maximum likelihood estimator method. And so that, as I said, this is beyond the scope, so I will not discuss that. Okay, so now our next target is to interpret the logistic regression model. That means how to interpret the coefficients. To do that, first we have to go through some basic probability concepts. So let's see what we have, and then we will try to understand how to interpret the logistic regression model. So first, note that for a binary variable with probability of success P, the probability of failure should be given by 1 minus P. Why? Because since it is a binary variable, it has only two possible outcomes. If the one outcome has a probability of P, then the other one should have the probability of 1 minus P. So now if you consider the ratio between P and 1 minus P, which is called as the odds. As you can see here, odds is equal to the probability of success divided by the probability of failure or the not success. So that is P over 1 minus P. So here, if you go back and here, if you see again, you can see this Px divided by 1 minus Px is exactly the same form as these odds. Now let's see some example. So consider the odds of having a head for a fair coin toss. So if the coin is fair, then the probability of having a head is 50%. So that means the probability of having a tail is also 50%. So our probability of success is 50%, probability of failure is also 50%. So the ratio will be equal to 1. So odds of having a head for a fair coin is equal to 1. The odds of having 1 or 2 when we roll a fair dice, what are the odds? So let's see. So if you roll a dice which is fair, then each dice has 6 sides. And since it is fair, each outcome, the from the 6 outcomes, each outcome has the equal probability. So having 1 has the probability of 1/6. Having 2 has the probability of 1/6. Likewise, having any outcome has the equal probability. So now here we are interested in having 1 or 2. So we have two ways to get that. That is having 1 or having 2. So our probability of success is 2 over 6. That is 1/3. So now what are the odds of having 1 or 2 if you roll a fair dice? So we know that the probability of success is 2 over 6. The probability of failure is 4 over 6. So then the 6 cancel out. So we have 2 over 4, which is 1/2. Okay, let's consider another example. Now suppose you have a coin which is not fair. So it is a biased coin. So suppose you have this coin with the probability of having head is more than 50%, let's say 60%. So then what are the odds of having a head in a coin flip? So then we know the probability of success is 60% and the probability of failure is 40%. So in this case, odds of having a head is 3 over 2, which is 1.5 times 1.5 or 150%. So the next concept is the odds ratio. As you can see, this name suggests odds ratio means having the ratio of two odds. If you look at this, for example, what is the odds ratio of getting head between the fair coin and the biased coin? So we know that the fair coin and the biased coin are having two odds to take the head. We know the odds of having a head for the fair coin is 1. Odds of having a head for the biased coin is 3 over 2. So if you consider the odds ratio having a head um, for the biased coin with respect to the fair coin, it is 3 over 2 divided by 1. So it is actually 3 over 2. So then how do we interpret this number? So this means actually uh, getting heads on the biased coin is 1.5 times more likely than the fair coin. So it is very important to understand this interpretation. And then we will talk about how to interpret the logistic regression model by using these concepts. Okay, so now we went through the basic probability idea. What are the odds and the odds ratio, how to interpret the odds ratio. So now let's see how we can interpret the coefficients of the logistic regression model. For simplicity, let's consider the simple logistic regression model. So this is very similar to simple linear regression model. The only difference is, so here you can see we have only one independent variable, and instead of the linear, um, our response variable now it is L log odds ratio. Sorry, it is a log odd. So we'll see. So you can see that in this model, we have only one independent variable. If we change it by 1 unit, that means we change x to x plus 1, for example, and take the difference. So here you can see my function is gx. So since I change my x to x plus 1 and then take the difference, so it gives me gx plus 1 minus gx. It will be equal to beta 1. So that is the coefficient of x. So this difference gives us the log value of the odds, the log value of the difference between the two log odd values, right? So here you can see that gx plus 1 minus gx is actually equal to the log value of uh, px1 divided by 1 minus px1 minus the log value px divided by 1 minus px. So here px means because this probability actually depends on x. So that's why I consider this probability as a function of x. If you apply the algebra of the logarithms, you can see that this log difference means actually the, the ratio of the two odds values. So that means you can see this gx plus 1 minus gx can be written as the log value of the odds of x plus 1 divided by odds of x. So this is actually the log value of the odds ratio, which is essentially equal to beta 1. So you can see now the logistic regression. In the logistic regression, the odds ratio for a given variable represents how the odds change for a unit change in that variable while all other variables held constant. So we can describe this beta 1, the coefficient of x, um, as in terms of the odds ratio. So let's see some examples so that you can have a better idea. So let's consider one example to digest the idea. Suppose we try to model the occurrence of getting a heart attack, and we find that the body weight variable has an odds ratio of 1.2. That is 1 pound increase of body weight. That means x to x plus 1 change. 1 pound increase in the body weight increases the odds of having a heart attack by 1.2. So the interesting thing here is we should note that this holds true for any unit increase for any initial body weight. If the body weight increase by 10 pounds, then the likelihood of having a heart attack is at least 6 times more. You can see that how did we calculate this 6 times is actually the 1.2 time 1.2 to the power 10, which is equal to 6.19. So that tells us if the body weight increased by 10 pounds, then it will increase the odds by 6 times. It is important to note that the actual probability of having a heart attack is lower for people with low body weight. Thus, even though the 10-pound increase would increase the odds 6 times, the probability will still remain low for people with low initial body weight. So this understanding is very important especially when you try to explain in your particular situation. So the odds and the probability are two different concepts. So here I have listed one exercise for you to try. So verify that if x changes from x plus m, that means if x changed by m units, what is the odds ratio for that change of x? Just confirm that you can get that number in this form by using your algebra knowledge. Okay, so now let's see how we can use real data to build a logistic regression model in R and how to interpret the results. In R, there is a package called Titanic, which can be installed in your computer to access the Titanic data. Titanic is a British luxury passenger ship that sank on 1912 by killing about 1,500 people. This is one of the most famous tragedies in modern history, which inspired movies, a musical, and scholarly work. We first checked for data quality and examined the data set to identify features with missing values and extremes. So here you can see, so this data set has 891 observations with 12 features. And so this head will give you the first few rows of the data set. And you can use the summary to get a summary for each feature. And then, so here I have listed the definition of each feature in this data set. Our objective is to fit a logistic regression model to predict if a given individual is a survivor or not using the age, sex, and the ticket class. So ticket class is P class, sex, and the age. So this is the code that we are using to fit the logistic regression model. And by using summary for this model fit, you can get the summary results. So just to give you a brief idea, here you can see the coefficients. We have three variables. So we have three coefficients, and this p-value for each of these coefficients are less than 5%. So they are statistically significant at the 5% significance level. And that means this model should be good. So we can see to calculate how to calculate the odds ratios, and then we will interpret these features or these coefficients. Okay, so using the given code, you can fit a logistic regression with those three features to predict the survival. In this model, we have the intercept, and it will give us the log odds of survived when the ticket class, age, and sex are 0. Each coefficient can be interpreted the way we interpret the coefficients in the simple logistic regression. For example, the coefficient of the sex variable indicates that the odds of survival for males are about 8% that of females. It's because if you look at the previous slide, here you can see the base category for sex is females. Therefore, everything is explained with respect to the base category. So when we increase the sex variable by 1, that means it is changing from female to male. We can see that all independent variables are statistically significant, as I said earlier, and we can confirm that by checking the confidence intervals. And also we can see that the age coefficient and p-class coefficient are negative. So the age coefficient and the p-class coefficient are negative. So what does that mean? That implies as age increases, the odds of survival decreases. And also the p-class coefficient is negative. That means as we go higher in the class, it has a more survival opportunity, right? The goodness of fit is measured by pseudo R square. And since it is about 33% in this particular case, we can conclude that the model fit well for the trained data set. Odds ratio. Okay, so now let's see what are the how we can compare the binary data by using different tools. The first one is the odds ratio. Odds ratio can have values equal to 1, greater than 1, or less than 1. So if the odds ratio equals 1, that means there is no effect. If it is greater than 1, that means it has increase in odds. And the risk difference is related to X, the regressors or the predictors. Risk difference means the probability difference of occurring between two groups of a given predictor variable. Positive risk difference implies an increase in risk. Absolute risk is the probability of occurring each level of a given predictor variable. Relative risk is the probability ratio of the event occurring between two groups for a given predictor variable. If relative risk is 1, then there is no effect. Positive relative risk indicates an increasing risk. Right, so let's see the multiple logistic regression. Multiple logistic regression is the extension of simple logistic regression model. Interpretation is very similar to that of simple logistic regression. Each coefficient shows the strength and the direction of the relationship between the log odds and the corresponding predictor. Always remember that the coefficient interpretation is specific to the context that we are interested in. Okay, so now we need to see how we select the model. So model selection means, in this case, actually the feature selection. By selecting different features, we can get different models. So how we can do the model selection? Model selection can be done in several ways. So here I will explain, or I will briefly introduce the most common approaches. So we can start only with the intercept, and then we can add predictors one at a time. So this method is called the forward selection. So in each iteration, we select the predictor that improves the model most, and we stop when further additions do not improve the model significantly. We can use adjusted R square to see if the accountability of the model is improved or not. The opposite approach is the backward elimination. So in this approach, We start with the model that has all the predictors, and we remove one at a time that has the least significance. We stop removing variables when further elimination do not improve the model significantly. Sometimes we combine the above two approaches together that call the stepwise selection. And also there are some other techniques such as regularization techniques like lasso, ridge regression, or elastic nets to do the feature selection. And also we can use the information criteria such as AIC or BIC. And also we use sometimes the cross-validation, likelihood ratio test, and also we use the domain knowledge when we select the most important variables. So it is very important to note that there is no set method for model selection, and the best approach may depend on the characteristics of your data set and the objective of your study. So there is a golden rule in statistics to remember, that is simpler the better. Okay, so now suppose you have finalized the features and you have fit the model. So now it is time to measure if the model that we fit is good or not. So that called the goodness of fit. So how do we measure the goodness of fit? In logistic regression, we can answer this question using different tools. Among them, the following are most common. We can use the deviance statistic to measure the goodness of fit. This is very similar to the residual sum of square we use in linear regression, and smaller the deviance, better the fit. Another tool is to use Hosmer-Lemshow test, which divides the estimated probabilities into several groups and compare the actual and the estimated probabilities in each group using chi-square test. Insignificant p-value in the test implies a good fit. Another tool is to use the area under the ROC curve, which measures the classification power of the model. High AUC implies a better fit. Residual analysis is an important test to see if there is any pattern or outliers. If the model is good, then there should not be any pattern in the residual plot. Information criteria values also can be used to select between models. Lower the value implies the better fit. So once we finalize our model and once we confirm the model is a better fit, we can start making the predictions. So note that the fitted model estimates the probabilities, but our objective is to make a classification. So how do we make the classification? By using our fitted model. In our logistic regression model, we have binary response variable. The estimated probability can be interpreted as the likelihood of occurring the success. By setting a predetermined threshold value, we can make classification based on the estimated probability. Suppose the estimated probability is 60% and we set our threshold as 50%. Then in this case, we classify this observation as a success occurrence. If the estimated probability is, let's say, 48%, for example, then based on our threshold value, which is 50%, we classify this observation as an occurrence of failure. In this lesson, so far we consider the binary response variable, but we can extend the same idea with a response variable which has more than two categories. So we called it a multinomial response variable. Multinomial logistic regression is also known as the softmax regression because it uses the softmax function to ensure that the estimated probabilities for each mutually exclusive category added up to 1. So the basic requirement when we deal with the probabilities is the summation of the probabilities should add up to 1. And in this case, we use the softmax function to make sure that we satisfy that requirement. For example, for a multinomial regression, we can think about classifying a patient's blood group as and one example for a multinomial logistic regression model. Then we can also extend the idea of logistic regression model to with the ordinal response variables. So up to this point, we consider only nominal variables as our response variable. For the completeness, I will briefly introduce the proportional odds model that is actually the logistic regression model for ordinal responses. If we have a response variable that is categorical by nature, but order matters like income categories, then we need to use proportional odds model to analyze such a case. Proportional odds model extends the idea of usual logistic regression model to handle response variables with more than two ordered categories. In this model, it assumes that the difference in the log odds between adjacent categories remains constant across all levels of predictors. You can, of course, further read about this model, which is a little bit a complex model. But for example, I would say, I will explain briefly about this model. For example, suppose we have a health rating as our response variable with categories poor, fair, good, and excellent. Then the model assumption implies that the odds ratio between the categories are consistent. First, we estimate the cumulative log odds of the response variable at a given level, and then use these log odds to calculate probabilities to predict the likelihood of falling into each category. This topic need to be further discussed in more details, but for this lesson, it is beyond the scope. Thank you.